Number 100 Facts About Time and Space, a Sleep Story. Hello there, and welcome to Cosmic Sleep Stories. I'm so glad you found your way here tonight. Maybe you've always wondered about the nature of time, why it flows in only one direction, whether the future already exists. Or perhaps you've been curious about black holes, those mysterious cosmic objects where space and time themselves break down. Either way, you're exactly where you need to be. You can rest now. Tonight, you have nothing to do but let go. Let your breathing slow, steady as the tick of a cosmic clock, deep as the fabric of spacetime itself. Let your body relax, feeling the gravity that holds you gently to Earth, that same fundamental force that shapes the universe. Let your mind drift outward, beyond the moment, beyond the familiar flow of time, into the strange realm where past, present, and future blur together, where time itself becomes just another dimension to explore. Over the next hour and more, we'll journey together through 100 gentle truths about time and space, those fundamental dimensions that form the stage on which everything happens. We'll explore Einstein's revelations about relativity. We'll dive into black holes where time stops and space becomes infinite. We'll contemplate the arrow of time, the possibility of time travel, the quantum mysteries that suggest reality is far stranger than common sense suggests. Some facts will astound you. Others will simply wash over you like waves in space-time, leaving only soft ripples as you drift toward sleep. There's no need to understand everything completely. Even physicists don't fully understand time and space. Just let the ideas flow through your mind like light through the cosmos, illuminating briefly, then fading into comfortable darkness. Let yourself be carried by the wonder of it all, by the deep strangeness of the universe we inhabit. And before we begin our journey through space-time, if these quiet cosmic explorations help you unwind at the end of your day, consider subscribing to Cosmic Sleep Stories. It helps others find this peaceful corner of the universe, one sleepy soul at a time. Now, close your eyes if you'd like. Breathe slowly, feeling yourself anchored to this moment, to this place, even as your mind prepares to wander through time and space. And let's begin our journey into the deepest mysteries of the cosmos. What is time? This seems like a simple question, something so obvious it barely needs asking. Time is what clocks measure. Time is what separates past from future. Time is the medium through which we move, always forward, never back, from birth toward death, from cause to effect, from memory to anticipation. But when you try to pin down exactly what time is, when you try to define it rigorously, it becomes elusive, mysterious, perhaps the deepest puzzle in all of physics and philosophy. St. Augustine, writing in the 4th century, captured this perfectly. What then is time? If no one asks me, I know what it is. If I wish to explain it to him who asks, I do not know. We experience time as flowing, as passing, as a river carrying us from past through present toward future. But is this flow real, or is it an illusion created by consciousness, by memory and anticipation? Does time actually pass, or do we simply move through time like walking down a road that already exists in its entirety? Physics offers no clear answer. In fact, the fundamental equations of physics, from Newton's laws to Einstein's relativity to quantum mechanics, work equally well whether time flows forward or backward. If you could film the microscopic world, atoms and particles obeying physical laws, and play the film in reverse, you couldn't tell the difference. The laws themselves don't prefer any direction of time. Yet we clearly experience an arrow of time. Eggs break, but don't spontaneously reassemble. Coffee cools, but doesn't spontaneously heat up. We remember the past, but not the future. Entropy, disorder, always increases in closed systems, never decreases. This is the second law of thermodynamics, one of the few physical laws that does distinguish past from future, that gives time its arrow. But why? Why does entropy increase? Why does time have a direction? The answer seems to be initial conditions, the state of the universe at the beginning. The Big Bang created an extremely low-entropy state, highly ordered, everything compressed into an infinitesimal point. Since then, the universe has been evolving toward higher entropy, greater disorder, and this evolution creates the arrow of time, the direction from past to future. Without the low-entropy beginning, without that special initial state, there might be no arrow of time. Events would be equally likely to run forward or backward. Eggs might spontaneously reassemble. Coffee might heat itself up. The past and future would be symmetric, indistinguishable. But because we live in a universe still relaxing from its extraordinary beginning, still expanding and evolving toward equilibrium, we experience time as flowing, as having a clear direction from low-entropy past toward high-entropy future. And yet, at a fundamental level, according to modern physics, time may not flow at all. Einstein's theory suggests that past, present, and future all exist equally, that the flow of time is an illusion, that the universe is better described as a four-dimensional spacetime where all moments exist simultaneously, laid out like frames in a film reel. We experience them one at a time, moment by moment, but that's a feature of consciousness, not of time itself. This is called the block universe view, and it's deeply counterintuitive, disturbing even. It suggests that your birth and your death both exist right now, eternally present in spacetime, that everything that will ever happen to you already exists in some sense. Free will becomes problematic. The future seems predetermined if it already exists. And yet this is what Einstein's theories seem to suggest, what many physicists believe, even if it contradicts our deepest intuitions about the nature of time. As you rest now, feel time passing or seeming to pass. Feel the present moment, this breath, this heartbeat, this instant of awareness. It seems so vivid, so real, so uniquely privileged compared to past and future. But according to physics, this moment is no more real than any other, no more special than yesterday or tomorrow. All moments exist equally in the block universe, in the four-dimensional space-time that is the arena of all existence. Does this disturb you, or does it comfort you? If all moments exist eternally, then nothing is truly lost. The past isn't gone, just inaccessible from our current perspective. The future isn't non-existent, just not yet reached. Everything that ever was or will be exists somewhere in the vast tapestry of space-time, preserved forever, eternal in a sense, even if we experience it as fleeting. Let this thought settle over you like a soft blanket. Time may be an illusion, or it may be real. The present moment may be special, or it may be just one point among infinite points, no more or less real than any other. Either way, you're here now, breathing, existing, experiencing this moment, and that's enough. That's everything. Let the mystery of time remain mysterious. Let the questions remain unanswered. And let yourself drift, relaxing into the flow or the illusion of flow, moving from waking toward sleeping, from consciousness toward dreams, carried by time or the appearance of time into the peaceful darkness ahead. In 1905, a young patent clerk in Switzerland named Albert Einstein published a paper that would revolutionize our understanding of space and time. He called it On the Electrodynamics of Moving Bodies, but it would become known as the theory of special relativity. And it revealed that space and time are not separate, absolute, fixed entities as Newton had believed, but are intimately connected, relative, flexible, woven together into a single fabric called spacetime. Einstein's key insight was that the speed of light is constant, always the same, exactly 299,792,458 meters per second, regardless of how you're moving when you measure it. This seems impossible, contradictory even. If you're in a car moving forward at 100 kilometers per hour and you shine a flashlight forward, common sense says the light should be traveling at the speed of light plus 100 kilometers per hour. But it doesn't. It travels at exactly the speed of light, no faster, no slower, as if your motion doesn't affect it at all. This bizarre fact leads to astonishing conclusions. If the speed of light is always constant, then something else must be flexible, must change to accommodate this constancy. And that something is time and space themselves. Time and space stretch and compress, speed up and slow down, depending on how you're moving. If you're moving fast relative to someone else, time passes more slowly for you than for them. This is called time dilation, and it's been confirmed countless times through experiments. Atomic clocks flown in airplanes run slightly slower than identical clocks left on the ground. Particles created in high-energy collisions live longer than they should because they're moving so fast that time slows down for them. Astronauts on the International Space Station age slightly more slowly than people on Earth, though the effect is tiny, measured in milliseconds, not enough to notice without atomic clocks. But at speeds approaching the speed of light, time dilation becomes dramatic. If you could travel at 99% the speed of light, time would pass 7 times slower for you than for someone stationary. A year of your time would equal 7 years for them. You could travel to a distant star and back and find that everyone you knew had aged decades while you aged only a few years. This isn't science fiction or speculation. It's experimentally verified fact, confirmed by countless observations. Time really is relative, really does depend on motion. There is no absolute time, no universal clock ticking away the same for everyone. Each observer has their own time, and these times can differ dramatically depending on their relative motion. Space is relative too. If you're moving fast, lengths contract in the direction of motion. A meter stick moving past you at high speed would appear shorter than a meter squeezed by your motion. At 99% the speed of light, it would appear to be only about 14 centimeters long. This isn't an illusion or a measurement error. The stick really is shorter from your perspective, as real as time dilation, another consequence of the constancy of light speed. And time and space aren't just relative, they're interconnected. What one observer measures as space, another might measure as time, depending on their relative motion. Space and time are aspects of a single unified entity, spacetime, a four-dimensional fabric where the 3 dimensions of space and 1 dimension of time are woven together inseparably. Einstein went further. In 1915, he published his general theory of relativity, extending special relativity to include gravity, and revealing an even more stunning truth. Gravity is not a force in the traditional sense, but a curvature of spacetime itself. Mass and energy curve spacetime, creating what we perceive as gravitational attraction. Imagine spacetime as a rubber sheet, stretched flat. Now place a heavy ball on the sheet. It creates a depression, a curve in the fabric. If you roll a smaller ball nearby, it will spiral toward the heavy ball, not because of any force pulling it, but simply because it's following the curved geometry of the sheet. This is gravity, according to Einstein. Mass curves spacetime, and objects follow the curves, moving along what are called geodesics, the straightest possible paths through curved space. The Earth orbits the Sun not because of some mysterious force reaching across empty space to pull it, but because the Sun's mass curves spacetime around it, and the Earth is simply following that curvature, moving in a straight line through curved space, which appears to us as an elliptical orbit. This is more than just a different description of the same phenomenon. Einstein's theory makes predictions that Newton's couldn't, predictions that have been spectacularly confirmed. General relativity predicted that light would be bent by gravity, and this was confirmed during a solar eclipse in 1919, making Einstein world famous overnight. It predicted gravitational time dilation, that time passes more slowly near massive objects, and this has been confirmed with atomic clocks at different altitudes. It predicted gravitational waves, ripples in spacetime caused by accelerating masses, and these were finally detected directly in 2015, a century after Einstein's prediction. General relativity is our best current description of space, time, and gravity. It's been tested countless times, in countless ways, and it always works, always matches observations to exquisite precision. Yet it's deeply strange, profoundly counterintuitive, suggesting that the stage on which everything happens, space and time themselves, is flexible, dynamic, curved by matter and energy, far from the fixed, absolute arena Newton imagined. As you rest now, feel gravity holding you gently against your bed, pulling you toward Earth's center. That pull isn't a force reaching up from the ground. It's the curvature of spacetime created by Earth's mass. You're falling, constantly, through curved spacetime, but the ground prevents you from completing the fall, pushing back with what we call the normal force. In a sense, you're always falling, always following geodesics through spacetime. It's just that the Earth gets in the way. Let this thought be simultaneously strange and comforting. You're not being pulled down. You're following the natural geometry of the universe, moving along paths carved into spacetime by the planet beneath you. You're part of the cosmic dance, following curves shaped by gravity, connected to everything through the shared fabric of spacetime. And as you drift towards sleep, as consciousness begins to fade, imagine yourself floating, weightless, following your own geodesic through the four-dimensional manifold of spacetime, curving gently through the night, carried not by effort, but by the natural geometry of existence toward the peaceful destination of sleep. At the heart of Einstein's general relativity lies a prediction so strange, so extreme, that Einstein himself initially didn't believe it. Black holes, regions of spacetime so severely curved that nothing, not even light, can escape from them. They're called black because no light emerges, holes because things can fall in but never come out, profound distortions in the fabric of spacetime itself. Black holes form when massive stars die. Stars shine by fusing hydrogen into helium in their cores, and this fusion creates an outward pressure that balances gravity's inward pull. But eventually, the hydrogen runs out. From massive stars, the core can fuse heavier elements, helium into carbon, carbon into oxygen, continuing up the periodic table until iron. But iron can't be fused profitably. When the core fills with iron, fusion stops. Without fusion pressure to hold it up, the core collapses catastrophically in less than a second. Protons and electrons are squeezed together, forming neutrons, and if the core is massive enough, not even neutron degeneracy pressure can stop the collapse. The core implodes all the way to infinite density, to a singularity, a point of zero volume and infinite curvature where spacetime itself breaks down, where the laws of physics as we know them cease to apply. Around this singularity forms the event horizon, a boundary in spacetime beyond which nothing can escape, not matter, not light, not information. The event horizon isn't a physical surface, not something solid you could touch. It's a point of no return, a one-way membrane in spacetime. Cross it, and you can never come back. Every possible path through spacetime, every possible trajectory, leads inward toward the singularity. There's no escape, not even in principle, not even if you had infinite power and infinite fuel. From a distance, outside the event horizon, a black hole's gravity seems normal, following the same inverse square law as any other massive object. If the sun suddenly became a black hole, which it won't because it's not massive enough, Earth's orbit wouldn't change. We'd still orbit at the same distance, the same speed. We'd just freeze in darkness without the sun's heat and light. But as you approach a black hole, things get weird. Time dilation becomes extreme. If you watch someone fall toward the event horizon, you'd see them move slower and slower, their clock ticking more and more slowly, asymptotically approaching but never quite reaching the horizon. It would take infinite time, from your perspective, for them to cross. You'd see them frozen, redshifted, fading away, but never disappearing. From the infalling person's perspective, though, nothing special happens at the horizon. They cross it in finite time, perhaps without even noticing the moment of crossing. But they can never return, can never send signals back out. They fall toward the singularity, experiencing increasingly powerful tidal forces as they go. These tidal forces arise because gravity's strength increases as you get closer to the mass. Your feet, closer to the black hole than your head, would feel stronger gravity, stretching you vertically while compressing you horizontally. For stellar mass black holes, these tidal forces near the horizon would be lethal, ripping you apart in a process gruesomely called spaghettification. For supermassive black holes, millions or billions of times the sun's mass, the horizon is so far from the singularity that tidal forces there might be survivable, though you'd still eventually hit the singularity and be destroyed. What happens at the singularity? We don't know. General relativity predicts infinite curvature, infinite density, conditions so extreme that the theory itself breaks down. Quantum effects, completely ignored in general relativity, should become important at such extremes, but we don't have a theory of quantum gravity to tell us what happens. The singularity represents the boundary of our knowledge, a place where our best theories fail, where we must admit ignorance. Stephen Hawking showed that black holes aren't entirely black. Through quantum effects near the horizon, they emit radiation, now called Hawking radiation, very slowly losing mass and eventually evaporating completely. For stellar mass black holes, this process takes far longer than the current age of the universe. But for microscopic black holes, if they exist, evaporation could be rapid. Hawking radiation is purely theoretical, never observed directly, but it suggests deep connections between quantum mechanics, general relativity, and thermodynamics. Black holes also raise profound puzzles about information. Quantum mechanics insists that information can't be destroyed, that if you know the complete quantum state of a system at one time, you can calculate it at any other time, forward or backward. But black holes seem to destroy information. Whatever falls in is lost, and when the black hole eventually evaporates, the Hawking radiation carries no information about what fell in. This is the black hole information paradox, and it's been debated for decades, with various proposed resolutions, but no consensus. Despite their strangeness, black holes are real, not just mathematical curiosities. We've detected them through their effects on nearby matter, through the X-rays emitted by gas spiraling into them, through the gravitational waves produced when two black holes merge. We've even imaged a black hole directly, or rather its shadow against the glowing gas around it. In 2019, the Event Horizon Telescope collaboration released an image of the supermassive black hole at the center of the galaxy M87, showing a dark circle surrounded by a bright ring, exactly as predicted by general relativity. Most galaxies, including our own Milky Way, have supermassive black holes at their centers, millions or billions of times the sun's mass. These monsters influence galactic evolution, regulating star formation, driving jets of material that stretch across millions of light years. They're not cosmic vacuum cleaners, not sucking in everything around them, but they do shape their galaxies profoundly, linking the growth of black holes to the growth of galaxies in ways we're still working to understand. As you rest now, as you drift towards sleep, imagine spacetime as a fabric, smooth and flat most places, but curved and warped by mass and energy. And imagine black holes as places where the fabric is torn, where curvature becomes infinite, where the familiar rules break down. They're windows to the edge of knowledge, to the boundary between what we understand and what remains mysterious. Let the strangeness of black holes be a lullaby, a reminder that the universe is far stranger than everyday experience suggests, that beyond the familiar world of clocks and calendars, forces and motions, lies a deeper reality where time stops, space curves infinitely, and the laws of physics themselves reach their limits. You don't need to understand it all. You can simply marvel, simply appreciate the profound mystery, then let it go, sinking back into the comfortable, comprehensible present moment, drifting towards sleep. Light travels fast, really fast. At 299,792,458 meters per second, light could circle Earth's equator more than 7 times in a single second. It reaches the moon in just over a second, the sun in about 8 minutes, the nearest star in 4 years. It's the fastest thing there is, and according to Einstein's relativity, nothing with mass can ever reach the speed of light, no matter how much energy you apply. Why? What makes the speed of light special? It's not just about light. It's about causality, about the structure of spacetime itself. The speed of light is really the speed of cause and effect, the speed at which information can propagate, the maximum rate at which one event can influence another. It's built into the geometry of spacetime, a fundamental constant like the Planck constant or the gravitational constant. As you accelerate toward the speed of light, strange things happen. From your perspective, everything seems normal. You feel acceleration, you burn fuel, you gain speed. But to outside observers, your mass increases, approaching infinity as you approach light speed. You need more and more energy to accelerate further, and you'd need infinite energy to actually reach light speed. It's not a technological limitation, but a fundamental barrier built into the structure of reality. Time dilation becomes extreme. At 99% the speed of light, time passes 7 times slower for you. At 99.9%, about 22 times slower. At 99.999%, about 224 times slower. Asymptotically approaching light speed, time dilation approaches infinity. From your perspective, you could cross the entire galaxy in what feels like minutes or hours, while billions of years pass for stationary observers. You'd see the universe age rapidly, stars being born and dying, galaxies colliding and merging, all in fast forward from your perspective. For light itself, for photons traveling at light speed, no time passes at all. From a photon's perspective, if we can speak of such a thing, its journey from emission to absorption is instantaneous, regardless of the distance traveled. A photon emitted by a distant quasar 13 billion years ago, traveling 13 billion light-years across the expanding universe, experiences no time during its journey. It's emitted and absorbed in the same instant from its own reference frame. This is why nothing with mass can reach light speed. At light speed, your mass would be infinite. You'd need infinite energy, and no time would pass from your perspective. You'd cease to be a meaningful physical object and become more like a geometric feature of spacetime itself. Only massless particles, photons and possibly gravitons, can travel at light speed, and they must travel at that speed, can never go slower, can never be at rest. The speed of light also creates a cosmic speed limit for information and causality. If something happens on the sun right now, we won't see it for 8 minutes, because that's how long light takes to reach Earth. We can't know about it any sooner because no signal can travel faster than light. The sun could explode, and we'd have 8 minutes of normal sunlight before we knew anything was wrong. This creates a fundamental limitation on simultaneity. Events that appear simultaneous to one observer might not be simultaneous to another observer moving relative to the first. There's no absolute now that extends across all of space. Each observer has their own present moment, their own slice through space-time, and these slices can differ. Simultaneity is relative, just like time and space themselves. This also means faster-than-light travel would be tantamount to time travel. If you could send a signal faster than light, if you could communicate instantaneously across distance, you could use this to send messages to your own past, creating causal loops and paradoxes. This is why physicists are so confident that faster-than-light travel is impossible. It's not just about engineering challenges, but about preserving causality, preventing paradoxes, maintaining the logical consistency of the universe. Yet physics doesn't absolutely forbid faster-than-light travel. General relativity allows solutions where space-time itself is warped in ways that could permit shortcuts, like wormholes connecting distant regions of space, or warp drives that compress space in front of a ship while expanding it behind. These are mathematically consistent solutions to Einstein's equations, but they require exotic matter with negative energy density, something that probably doesn't exist, and even if it did, the energy requirements would be astronomical, perhaps requiring more energy than exists in the entire observable universe. So while we can't definitively rule out faster-than-light travel, it remains firmly in the realm of speculation, probably impossible, certainly beyond any technology we can currently imagine. For now, and probably forever, we're limited by the speed of light, confined to our local region of space-time, unable to reach most of the universe within any reasonable time frame. As you rest, imagine light traveling, photons streaming across the cosmos at their maximum speed, carrying information, carrying energy, connecting distant events through causality. Every photon that enters your eye has traveled from somewhere, a lamp, a star, a galaxy billions of light years away, carrying with it information about the past, about events that happened light years or billions of years ago. Right now, in the darkness behind your closed eyes, the last photons of the day have been processed by your visual cortex. The light from your room, from the setting sun, from distant stars, all of it has reached you at exactly the same speed, all traveling at the cosmic speed limit, all obeying the same fundamental laws. And as you drift towards sleep, as the external world fades, the light fades too, leaving only darkness, peaceful and complete. Traveling through time has captivated human imagination for centuries, from ancient myths to modern science fiction. We dream of visiting the past, of witnessing history firsthand, of perhaps changing events, correcting mistakes. We wonder about the future, what it holds, whether we could skip ahead to see how things turn out. But is time travel possible? Does physics permit it? Or is it forever confined to fantasy? The surprising answer is that time travel to the future is not only possible, but actually happens, routinely, though not in the dramatic way science fiction depicts. Every time you move, you travel through time at a slightly different rate than someone stationary. Every time you ascend a mountain, time passes slightly faster for you than for someone at sea level. These effects are tiny, measured in nanoseconds or microseconds, but they're real, verified by atomic clocks, predicted by Einstein's relativity. If you want to travel significantly into the future, You need to move fast, very fast, approaching the speed of light. At such speeds, time dilation becomes dramatic. You could travel on a spaceship at 99.9% the speed of light for what feels to you like a year, then return to Earth to find that 22 years have passed. You've traveled 21 years into Earth's future in just 1 year of your own time. This isn't speculation or theory. It's a direct consequence of special relativity, as well established as any scientific fact. The practical obstacles are enormous, of course. Accelerating even a small spacecraft to near-light speed would require staggering amounts of energy, far beyond our current capabilities. And the faster you go, the more dangerous space becomes. At high speeds, even tiny dust particles become devastating projectiles, hitting with enormous kinetic energy. And cosmic radiation becomes more intense, potentially lethal. These are engineering challenges, not fundamental physics, but they're severe enough that near-light speed travel remains far beyond our reach. Alternatively, you could travel into the future by approaching a massive object like a black hole, where gravitational time dilation is extreme. Close to a black hole's event horizon, time passes much more slowly than far away. You could orbit just outside the horizon for what feels like a few hours, then escape to find that years or decades have passed for the outside universe. Again, this is real physics, not science fiction, though the practical difficulties are immense. Traveling to the past is more problematic. Physics doesn't absolutely forbid it, but it's much more constrained, much more difficult, perhaps impossible. General relativity does allow solutions where closed time-like curves exist, paths through spacetime that loop back to their own past. These solutions involve rotating black holes, wormholes, or exotic spacetime geometries, and they're mathematically consistent with Einstein's equations. But do such solutions exist in reality? Can they be created? Would they actually allow backward time travel? These questions remain open, hotly debated among physicists. Most suspect that some principle, perhaps related to quantum mechanics, prevents closed time-like curves from actually forming, preserving causality and preventing the paradoxes that backward time travel would create. The most famous paradox is the grandfather paradox. If you travel to the past and prevent your grandfather from meeting your grandmother, you would never be born, which means you couldn't travel to the past to prevent the meeting, which means you would be born, which means you could travel to the past, creating an impossible causal loop. Many proposed resolutions exist, from multiple timelines to self-consistency principles, but none is entirely satisfactory. Stephen Hawking proposed what he called the chronology protection conjecture, that the laws of physics conspire to prevent backward time travel, to protect causality from paradoxes. He didn't prove this rigorously, but he and others showed that attempts to create time machines, like using wormholes, seem to lead to runaway quantum effects that might destroy the time machine before it can function. Nature, it seems, might have a way of preventing paradoxes, of ensuring that the past remains fixed, unchangeable, safe from meddling time travelers. Yet the future remains open, unwritten, at least from our perspective. Special relativity suggests the block universe view, where all moments exist equally, past and future already laid out in the four-dimensional spacetime manifold. But quantum mechanics suggests true randomness, true unpredictability, outcomes that aren't determined until they happen. The tension between these views, between determinism and indeterminism, between block universe and open future, remains one of the deep conceptual puzzles in modern physics. Perhaps the past is fixed and the future open. Perhaps both are fixed and the appearance of openness is an illusion. Or perhaps time itself is more flexible, more strange than we currently imagine, with properties we haven't yet discovered, possibilities we haven't yet conceived. The full nature of time remains mysterious, and time travel, backward at least, remains in the realm of speculation, tantalizing but probably impossible. As you drift now, let go of the past. It's gone, inaccessible, fixed in the block of space-time if the block universe view is correct, or simply vanished if time truly flows. Either way, you can't change it, can't return to it, can only remember and learn from it. And let go of the future too. It hasn't arrived yet, doesn't yet exist in any meaningful sense from your current perspective, isn't something you can see or touch or influence except by the choices you make in the present. There's only now, this moment, this breath, this gradual relaxation into sleep. The past is behind you. The future is ahead. And you're here, in the present, the only time that's fully real, the only moment you actually inhabit. Let that be enough. Let the mystery of time remain mysterious. And let yourself drift through the only direction you can go. Forward, from waking toward sleeping, from consciousness toward dreams, carried by the irreversible flow of time toward rest. In the bizarre realm of quantum mechanics, the rules that govern the macroscopic world break down. Particles exist in superpositions, being in multiple states simultaneously until measured. They display wave-particle duality, behaving sometimes like particles, sometimes like waves. They're entangled, mysteriously connected across arbitrary distances. And time itself becomes strange, less absolute, more malleable than classical physics suggests. In quantum mechanics, the future is genuinely undetermined. When you measure a quantum system, when you observe which slit a photon went through or what spin an electron has, the outcome is truly random, not just unknown, but actually undecided until the moment of measurement. Einstein hated this, famously declaring that God does not play dice, but experiment after experiment has confirmed quantum randomness. The universe really does have built-in unpredictability at its foundation. This means the future isn't written in the present. Unlike classical physics, where knowing the exact state of everything now would let you calculate everything that will happen, quantum mechanics says the future contains irreducible uncertainty, outcomes that aren't determined by the present, that emerge only through the act of measurement or observation. Yet quantum mechanics also allows something stranger, retrocausality, where future events seem to influence past ones. The delayed choice quantum eraser experiment, first proposed by Wheeler and later performed, shows that a choice you make about how to measure a photon can affect the behavior that photon displayed earlier, before you made the choice. It's as if information can flow backward in time, as if the future can reach back to influence the past. This doesn't violate causality in the usual sense. You can't send messages to the past or change history. The effects are subtle, visible only in statistical patterns, not in individual events. But they suggest that quantum mechanics has a different relationship to time than classical physics, that past and future are less distinctly separated at the quantum level, that time's arrow might be less fundamental than we think. The Wheeler delayed choice experiment asks, when does a photon decide whether to be a particle or a wave? The answer seems to be, not until it's measured, even if that measurement comes after the photon has already passed through the apparatus. The photon doesn't have a definite particle or wave nature until observation collapses its wave function, and this collapse can retroactively determine behavior that seems to have already happened. These experiments don't prove that the future influences the past in any simple way. They're compatible with the block universe view, where all moments exist simultaneously and the appearance of temporal sequence is somewhat illusory. They're also compatible with interpretations where wave function collapse is non-local in time, happening not at a specific moment, but across an extended region of spacetime. Quantum entanglement adds to the strangeness. When particles are entangled, measuring one instantly affects the other, regardless of the distance between them. Einstein called this spooky action at a distance and saw it as a flaw in quantum mechanics. But experiments have confirmed entanglement countless times. It's real, though it can't be used to send information faster than light, so it doesn't violate relativity. What does entanglement mean for time? If particles can be correlated across space instantaneously, can they be correlated across time too? Some physicists think yes, that entanglement can link moments of time just as it links points in space, that the present moment might be quantum mechanically entangled with past and future moments in ways we don't yet understand. This could help resolve some puzzles about quantum mechanics and relativity, about how to reconcile the instant collapse of wave functions with the relativity of simultaneity, about how to build a quantum theory of gravity where spacetime itself is subject to quantum uncertainty. But these ideas remain speculative, far from proven, leading edges of theoretical physics where mathematics and philosophy and experiment all come together in attempts to glimpse deeper truths. The full theory of quantum gravity, whatever it turns out to be, might reveal time to be even stranger than current theories suggest. Some approaches, like loop quantum gravity, suggests spacetime is granular, made of discrete chunks rather than being continuous. Others, like string theory, require extra dimensions beyond the familiar three of space and one of time. Still others suggest time might be emergent, not fundamental, arising from more basic quantum information processes. We don't know which, if any, of these approaches is correct. We don't have a complete theory of quantum gravity, don't understand how to merge general relativity's smooth curved spacetime with quantum mechanics' discrete, probabilistic world. This is one of the greatest open problems in physics, pursued by thousands of researchers, still unsolved after decades of intense effort. As you rest now, let the quantum strangeness be background music to your descent into sleep. You don't need to understand it. Even physicists don't fully understand it. Just let it be there. A reminder that reality is deeper and stranger than everyday experience suggests, that beneath the surface of familiar cause and effect lies a realm where past and future blur, where particles are waves and waves are particles, where nothing is certain until it's observed. Let your own state remain quantum, superposed between waking and sleeping, between consciousness and dreams. You don't need to collapse into one state or the other just yet. You can remain in superposition a little longer, drifting in the liminal space between, suspended in possibility, relaxed and peaceful, and not quite decided about whether you're awake or asleep. And eventually, gradually, inevitably, the wave function will collapse. You'll transition from superposition to a definite state, from uncertain to certain, from waking to sleeping. But for now, you can hover in between, quantum and classical at once, enjoying the ambiguity, the lack of definition, the soft uncertainty that precedes sleep. Will time go on forever? Does the universe have an end, a final moment beyond which nothing more happens? Or does time stretch infinitely into the future, world without end, eternally evolving? Cosmology offers tentative answers, though certainty remains elusive. The universe began in the Big Bang, approximately 13.8 billion years ago. Before that, time itself may not have existed, or may have had different properties, or may have been part of a larger multiverse structure. We don't know. Our physics breaks down at the moment of the Big Bang, just as it breaks down at black hole singularities. Since the Big Bang, the universe has been expanding, galaxies moving apart, space itself stretching. For a long time, cosmologists thought this expansion would eventually slow and reverse, gravity pulling everything back together into a big crunch, the mirror image of the Big Bang, returning everything to a singularity where time would end. But observations in the late 1990s revealed something unexpected. The expansion is accelerating, not slowing. Some unknown force, dubbed dark energy, is pushing the universe apart faster and faster. This changes everything. If dark energy persists, if the acceleration continues, the universe will expand forever, never collapsing, never ending in a big crunch. Instead, it faces a different fate, the big freeze or heat death, where expansion eventually spreads everything so far apart that no new structures can form, where stars burn out and aren't replaced, where black holes evaporate and galaxies dissolve, where the universe becomes cold, dark, empty, approaching maximum entropy. In this scenario, time continues forever, but nothing interesting happens after a certain point. The universe reaches equilibrium, maximum disorder, and stays there eternally. Time still exists, still passes, but every moment is identical, featureless, devoid of change or structure or information. It's not so much an end to time as an end to time's meaningfulness, an eternal flat line extending forever. Other scenarios exist. If dark energy changes, if it weakens or reverses, the big crunch could still happen, bringing time to a definite end. Or if dark energy strengthens, the big rip could occur, where acceleration becomes so extreme that it tears apart galaxies, stars, planets, atoms, even nuclei, shredding the fabric of spacetime itself, perhaps ending time in some catastrophic rupture of reality. These are cosmological timescales, billions or trillions of years in the future, far beyond human concerns. The sun will die in about 5 billion years, swelling into a red giant and engulfing Earth. The last stars will burn out in perhaps 100 trillion years. Black holes will evaporate over timescales so vast they're hard to comprehend, 10 to the power of 100 years or more. These numbers are so large that they lose meaning, becoming abstract, more like infinity than like anything experiential. Yet, even if time goes on forever, even if the universe never ends, our time is finite. You have a limited number of heartbeats, breaths, days. This moment will pass, this day will end, and eventually, inevitably, your time will run out. This is simultaneously sobering and liberating. Time is precious because it's finite. Moments matter because they're temporary, fleeting, never to return. As you rest now, feel the preciousness of this moment. It's finite, bounded, surrounded by the infinities of past and future, but itself singular, unique, unrepeatable. This exact configuration of you, here, now, breathing, listening, existing, will never happen again. Every moment is a small death and a small birth, the previous moment dying away, the next moment not yet arrived. Only this instant truly real. Let that be okay. Let the finiteness of time be acceptable, even beautiful. You don't need eternity. You have now, and now is enough. Let the vast cosmic timescales, the billions of years past and future, let all of that fade into comfortable irrelevance. You live in a thin slice of time, a brief interval between birth and death, and within that interval, you have right now, this moment, this breath. And right now, you're drifting toward sleep, toward the nightly erasure of consciousness, the temporary end of your subjective time. In a few hours, you'll wake, time will resume, but for now, let it go. Let time stop mattering. Let past and future dissolve. Let there be only the eternal present of deepening rest, the timeless now of sleep approaching, the soft darkness that has no duration because you won't be conscious to measure it. And now, as we approach the end of our journey through time and space, let's return to where we started, the present moment, the eternal now, the only time you ever truly inhabit. Past and future are abstractions, mental constructs, memories and anticipations, but they're never directly experienced. You only ever live in the present, in the thin moving boundary between what was and what will be. You've traveled far tonight, through Einstein's theories and black holes' mysteries, through the speed of light and the possibility of time travel, through quantum strangeness and cosmological futures. You've contemplated time's nature, space's curvature, the deep structure of reality itself. And through it all, you've remained here, in this moment, reading or listening, breathing, existing. The universe may be a four-dimensional space-time where all moments exist equally. Or time may truly flow, carrying you irreversibly from past toward future. The debate continues, unsettled, perhaps unsettlable. But regardless of which view is correct, your experience is the same. You live in the now, the present moment, the only time consciousness can occupy. And right now, that present moment is peaceful, quiet, relaxing. Your body is at rest, supported by your bed, held by gravity, comfortable and still. Your breathing is slow and deep, automatic, requiring no thought or effort. Your mind is drifting, thoughts becoming less coherent, the sharp focus of waking awareness softening into the diffuse, dreamlike quality that precedes sleep. Time seems to slow when you're relaxed, when you're not doing anything, when you're simply being. Without tasks to mark its passage, without events to segment it, time becomes smooth, undifferentiated, almost disappearing. The present moment expands, filling awareness, leaving no room for past or future, only the soft, eternal now of rest. This is the paradox of sleep. It takes time, hours passing on the clock, but from your perspective, subjectively, no time passes at all. You close your eyes, and then you open them, and it's morning, and the intervening hours have vanished, collapsed into nothing, as if they never happened. Sleep is a daily encounter with timelessness, with the cessation of subjective time, with the eternal present of unconsciousness. As you drift there now, toward that timeless realm, let all the facts and theories and mysteries of time and space fade away. Let Einstein and black holes and quantum mechanics all recede into comfortable distance. They'll still be there tomorrow, still fascinating, still mysterious, but for now, they're not important. Nothing is important except this. the soft descent into sleep, the gradual dissolution of consciousness, the gentle letting go of everything, including time itself. Your breathing slows. Your heartbeat quiets. Your thoughts become sparse, fragmentary, disconnected. This is the transition, the crossing from time into timelessness, from the world of clocks and calendars into the eternal now of sleep, where past and future don't exist, where only the unchanging present remains, dark and peaceful and complete. Let yourself cross that boundary. Let waking consciousness release its hold. Let time stop, or seem to stop, or become irrelevant. For the next few hours, you'll be outside time in a sense, beyond its reach, untouched by its flow. And when you return in the morning, time will resume. The world will continue, but you'll be rested, restored, renewed by your nightly sojourn in the timeless realm of sleep. Good night. Rest well. And let time itself rest too, released from the burden of flowing, suspended in the eternal now of sleep, where nothing changes because nothing needs to change, where everything is perfect and complete and still, forever and ever, in the endless present moment of peaceful rest.